All right, good morning again. Well, I guess morning for me, hopefully it's evening for you. 'Cause this is not, again, disclaimer, this is not a tutorial, I'm not teaching anything, but we're just working through some problems just for funsies. So we're going to do number 77 right here, and this is on page 80. So this section is the section's on independence, and I know independence is going to be defined as the probability doesn't change given a certain event. So yeah, if the probability of A given B is equal to the probability of A given B equal to just the probability of A. And this is also going to change some things as well. The multiplication rule. We know that is typically going to be the probability of A given B, and then multiply that probability of B. But given that we have the A given B is now probability of A, the multiplication rule in this case becomes the probability of A and the probability of D. And again, this is when we have an intersection between the two events happening. Equal. Okay, so I think these are the main points of the chapter. Let's just get over real quick. We're going to look at 77. An aircraft seam required 25 rivets. The seam will have to be reworked if any of these rivets is defective. Suppose rivets are defective independently of one another, each with the same probability. And A, if 20% of all seams need reworking, what is the probability that a rivet is defective? I'm going to be in a minute. Okay. Well, first of all, I don't even know what a seam or a rivet is. I leave you guys here. I got my computer right here. Let me take a look. So, again, as I said previously, the key to any math problem is going to be understanding the situation and knowing what we're given, and that will allow us to, the solving part will be relatively easy. But we got to understand what it's action. An aircraft, SCAM, aircraft seam, okay. The junction where two pieces of aircraft material, such as the metal skin, composite panels, or fabric, join. Rivets. So what are rivets then? What are rivets? A permanent, non-threaded mechanical fastener with a smooth cylindrical shaft with a head on one end. Okay, so I guess it's so maybe it's maybe the scenario is action about we have two pieces of maybe metal on a wing, and then we have so this would be like the seam down the middle, and then you would have to put these things called rivets, which are like kind of like nails, I guess, along the seam. Interesting. Okay, I haven't We'll just go with that. So let's look at the problem again. So a seam requires 25 rivets. Okay, and then the seam will need to be reworked if any of these rivets is defective, so any one of them. Okay. Suppose rivets are defective independently of one another, each with the same probability. If 20% of all seams need reworking, what is the probability that a rivet is defective? Okay. Let's go ahead and define the universe we're in. Let's define omega for the scenarios here. Okay, so I'm gonna guess that omega is going to be the each seam, yeah, I think each seam, or each seam, or it's going to be each individual seam with those 25 rivets. What would be the rivets? This is a tricky one. Rivets. We want to know the probability that a rivet is defective. So, it's asking for the probability of an event, and this event must be a subset of omega. So, but the probability that an individual rivet wouldn't be represented by a subset of the seams. Okay, so what we may need to do here is what I'm wondering is maybe the omega is each individual rivet. Each individual rivet, and then each aircraft seam, for example, seam 1, Okay, maybe we're getting it. So, seam 1 is essentially 25 of these rivets. So 25 rivets. So this is 25 elements. The size of seam 1 is 25. Okay, so this is the individual rivets, not just literally the word 25 rivets. And then we have another seam, and that's also 25 rivets. And so on. And we have 20% of all seams need reworking. So we know if an individual rivet, one of these rivets fails, then the seam needs to be reworked. How do I represent that? Maybe what we'll do is, so we have each individual rivet. Maybe what we'll do is we'll split it into two classes. Because really, depending on time, well, I guess it's saying it's defective. So not necessarily that the rivet became defective over time, but that it actually left the factory defective. Okay, so that's, I think we're getting there. So maybe we'll have the rivets that are good and the rivets that are bad or defective. Okay, RG, RB. And we'll split these into two classes so that essentially the good rivets and the red units union together will make our omega set. Okay. So let's see here. Let's have, we need a way to represent 20% of all seams need reworking. And so let's have another set S equal the set of, I guess, all of these, all seams, right? And the, and then we can split this and sort of an FG and an SB as well, meaning this is good, this is bad, so that yeah, I think that may actually so the probability of having a bad seam, these are seams, so this would be a different universe. Hold on. Yeah. Oh man. Let's say SB giving us, I don't know, something like that. But we know this is going to be 0.20. There's something I'm missing. Rivets are defective independently of one another, each with the same probability. Okay. Okay, each defective independent. Okay. Light went out. Got the light back on. Okay. Alright, so suppose that the size of our omega is n. So if they're all the same probability, could it be that they're 1 over n? No, they're not this. Well, they have, okay. Well, if each rivet had the same working it out. See if we can start writing it out again and just see if we can maybe come up with some new ideas here. So first of all, I think we'll keep the omega. Omega is each individual rivet. Okay, and then we'll define RG to be bigger than rivets. And then we'll define RB to be our bad rivets. And then the probability that we have a bad rivet going to simply be what is it? The size of omega on over the size of B, right? Don't know what that ratio is, but we do know that they are defective independently of each other. So that means it has something to do with this probability of multiplication. What if I do define a seam with those 25 rivets? Then we say that the probability of that we have a average that intersects with the S1. So that would mean that one of these rivets, or in the set of bad rivets, is equal to the probability of having a bad rivet times the probability of S1 in general. Or maybe it's saying that the probability in general of B intersect with any particular is gonna be equal to 0.2. So I want to know this, the probability of RB equal to 0.2 over the probability of right? And the probability of S1 well, you know the size is 25. So that would be 25 over the size of a meter. So E equals 0.2 divided by 25 over whatever a meter is, right? Should be equal to 0.2. Divided by 25 times size of a mega. This is equal to 0.2 divided by 25. 0.008. Then Okay. So let's say that I guess yeah, I'm confusing myself here. Okay. Okay. Here's the issue. The rivets are defective independently of one another. So did that mean? Because what this is, so what I'm getting stuck on here is that this omega is implying that basically the more rivets I have, I guess the higher, the more the probability for the probability increases for for it to have a bad rivet, which isn't making sense. Because I defined, hold on, so I defined, we got good rivets and bad rivets, right? And the probability that we have an intersection between this and this is the probability of just having a bad rivet in general, or with the probability, about times the probability that we have, what do you call it, 25 rivets or whatever we're charging. And we assume that's a random fact. Now, that's what we want to know. Oh, you know what? I changed, man. I think I changed this right here. I think it's supposed to be and that's why you show every step. Let me, let's redo it from here, but because I put the 1 instead of n. So the probability of that rivet in, that's n, okay, it's equal to 0.2. Now what we can say, given that these are an independent, kind of deal, that it's simply going to be the probability of the bad times the probability of Sn, not S1. That should equal to 0.2. Now, the probability of the probability of this in general think that didn't change anything, does it? This is still going to be a side 25 over this off again. Okay. So I guess, let's suppose we made a total of, let's just play around a little bit. Let's say we made a total of 10 rivets. No, let's do 100. All right, let's say I made 100. Then, according to this formula that we seem to be running on, the number of bad would be 100 squared 25 equals 0.2. And then, the number of bad would be essentially 2 100 squared by 25, right? So 80. Right? And so that's not correct. Yeah, what am I getting wrong? Alright, well, let's keep it moving and keep trying to get this figured out. Alright. Alright. To find omega, I think our omega's right. I think it's each individual rivet. Okay. And I do think that we do partition the set into RG, which is our good rivets, and our RB, which is our bad rivets. Okay. Do you think we do that? And we want to know what we want to know is the probability of RB. Is what we're looking for. Probability that a rivet is defective. Now, we have seams that are in use. And that these seams, Sn, is a subset of our omega what if the experiment is, what if we approach it as we have S, and this pulls out 25 random rivets. Okay. And we know that the we know that the accepting a mission. What if, could it be? Could it be that we could partition omega? We can play with this and see where it goes. What if we partition omega into a union of equals 1, 2, into a union of Sn? Okay, so we partition omega into a union of Sn. And we know that S1 dot 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 through Sn are disjoint. Therefore, this union should be according to the law of, this is the law of total probability. I don't know if the law of total probability was in the chapter or not. I didn't check. Probably should have. But, okay, so a disjoint. Then the probability then we know the probability of RB is equal to the sum, I equal to an n, but the probability of getting a bad rivet given we're in this, what do you call a particular thing, all over the probability that we are whatever that thing that is, like that sum. So maybe what's independent? The rivets are defective independently by another show. Well, I guess. Maybe there's a, let's see, probability of a bad. I'm confused whether or not the 20% of all scenes need rework, and that means that given the theme, the probability of having a bad rivet. Alright. Oh man, this is really dumping me. Alright, I'm gonna have to wave the white flag and I think get some extra help here. So I haven't read the chapter, so I'm, kind of not sure what to do here. What I like to do is I like to use a specifically programmed GPT to kind of help me reason through them. It doesn't do answers because GPT won't work in that regard, but it does look at kind of the overall connections and concepts. So since this is a problem that may show up in literature, I'm sure this is certainly going to be something that a GPT could push in the right direction. So what we'll do here is, let's see. I'll go ahead and scan it. And then we're going to scan the problem as well. Alright, let's make sure we got this. No, we need to redo this one. Let's see. No, why does it keep? As we check the page. And I think that one worked. Alright, and so what we do is we go ahead and get this to GPT and just see kind of what guidance, what direction you need to move in. Because this drives me a little bit nuts, but we're going to figure it out. How part of the mathematics? All right. Let's see. See if we can get some kind of good information here. Ooh. Okay. Oh, man. All right. All right, we need some GPT, we got some guidance here, and so we're gonna, it's like a mess, but we're gonna try to define omega in a little bit of a different way. So GPT trying to push us in the direction of thinking about this like a random, what is the same, what is the random experiment? Random experiment. And the omega is the omega, the possible outcomes. Possible outcomes, so I guess an outcome should essentially then be describing whether we have a whether it's good or it's bad, effective, and maybe this could be a, what do you call it, 25 different sort of combinations of this. So any combination of G and B. So really what this may look like is, so first of all, G equals, good with it, bad with it. And then we have one outcome that equals something like, G dot B, G. And this is a size of 25. That's so this represents all possible combinations of something like that. So so we have, so essentially there's one outcome that is good. That's we're okay. So this would be the outcome of G, 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 dot, 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 comma, G, G, and this is, and again, 25. So, and then RG, the complement, it's all bad outcomes. All bad outcomes, the at least one rivet is bad. Okay, I think we're getting somewhere here. Cool. So now we have the setup. Let's see if we can actually see if this setup is actually useful for us, so we can use it. So we're going to say that the probability of us having, or the probability of RG is simply going to be 0.8, and the probability of RG complement is simply going to be 0.2. And according to A, 20% need reworking, meaning in that thing. Okay. Now, what we want to know is the probability that any rivet is defective. So how do we represent that? And let me see here. I might need to. So how do we? Okay. Whew. So okay. So Man. We have suppose we have di, and we're going to put omega such that the ith rivet is bad. Okay. So in this case, D1 would mean the word that first rivet is defective. D2, so on. So the so essentially the probability of any DI being defective idea. Whatever. Idea. Okay. The probability of suppose the probability of any individual rivet is P. Suppose it's P, then obviously, the probability, we check each rivet. Okay, so we got some eyeballs. Ooh, we're checking each rivet. And the probability of each one being defective is going to be P, 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 P. Now, we know that the probability of this rivet, rivet 1, the probability of rivet 2 times the probability of rivet 3 will give me that overall probability there, right? I mean, that's the invisible thing. So this would be essentially be equal to a P to the 25. P to the 25 probability of a seam needing rework. So in essence, this would be, P to the 25 equals 0.20, and then, I would say P, that would be, let's see here, okay, 25, 2, we get a probability of what, 0.938, which is not good. Oh, right. Well, a problem is good when when the camera dies because you've been filming so long. Okay. I think when you're getting closer with this, and I want to continue to follow based on what we have here. Here we go. Let's do this. We're going to find our omega to be our combination of G's and B's in 25. Okay. And we are going to define let's see here. We're gonna define RB to essentially mean that we have at least one defective. And then RB complement is G, 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 dot, 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 G. Yeah. All right. So first of all, we know probability of RB at least one is defective at 0.2, and the probability of RB complement is therefore 0.8. Now, we can use what we were trying to do before with the let's go ahead and try it. We have di equals it's just that the if whether is defective and then what will happen here, we'll have R B is simply going to be the union of all of DI's. The union of all these sets, and we can also see here. So then the RBC, the complement, the intersection of the complements. Yeah, I think so. And then therefore this would be 0.8. The probability of any individual whoever being defective of anything is a constant, right? same probability, so they're independent as well. So if we presume this, then that would mean we have a product equals 1 to 25 of the probabilities of DIC. So we go our product 1 to 25 of 1 minus P, 1 minus P to the fifth power. Okay. And then we have okay. That would mean essentially we have the probability of RBC, which is equal to 1 minus P to the 25th power, which is equal to 0.8. So what we'll do is 1 minus P equals 25 root of 0.8. Obviously we'll just switch these around, so we have P equals 1 minus the 25th root of 8, which equals, let's see, so now this is where we get this. Nine, and so this probability here is the probability of an individual defective. Oh man, I can't believe it. Okay. And so this is a let's see, the camera's still going. Okay, good. Unbelievable. Okay, so we got a, and then B is action, how small should the probability of a defective rivet be to ensure that only 10% need reworking? Okay, so we basically want this to be 0.9, right? So this is page 80. Yeah, that's page 77. Let's see. Okay, my bad. So essentially saying we want that the we want our DC to have a good 90% shot. So what we would do now is we would say we need that probability to get down to, and now let's see, to the 25th. Hold on. That's 3.00421. That's the probability we put down for. Okay, and we'll check to make sure these answers are right. If they're not, then we stop in that side. Chapter 2. Oh, no, it's a very sad day. 0.06235 and then 0.00421. Wait, what? How D correct? We didn't get A. Huh? I didn't make it. What? Um, I am very confused. Maybe it's name the book probably this one, Engineering and Sciences, 7th edition. Maybe there's an error. Man. Let's see here. Let me look it up. There is an error. Sciences. This is the 7th edition. There is. Let's see here. I don't know if I'm going to be able to look it up here at the school because I can't download. Let's see here. So we're on chapter 2. Let's see here. Okay, I think I found a solutions manual. See if this is. it does appear to be a, oh, I can't show you, but it does appear to be a misprint. Yeah, so A is supposed to be 0.009 and B is supposed to be 0.004. So, oh man, that would be very sad if we didn't make that. Okay, so, and obviously the answer is a lot simpler done, but we're looking at it from a set theory point of view. We're trying to rigorously define our universe, our mega, our simple spaces, and try to do this rigorously. And it's not, what do you call them? The calculations, you can do relatively quickly and easily, but to really have a model of the situation, man, and I'm still not 100% convinced on this model, but I think we're very close to what it needs to be. So anyway, that was a math problem. All right, well, hopefully the problem tomorrow morning doesn't take as long as this. Hopefully this is an enjoyable experience for you. Thank you very much for watching. Please like, please subscribe, and I'll keep it up. Have a good evening.